The world of AI keeps moving fast, and every once in a while something comes along that shifts how we think about what these systems can do. One of those breakthroughs is something called BSTAR. Now the name might sound fancy, but the idea behind it is surprisingly practical, helping AI models teach themselves better without needing massive amounts of human-generated data. Here's the challenge: as AI models get smarter, their appetite for high-quality data keeps growing. Whether it's solving complex math problems, writing code, or even understanding basic logic, these models usually depend on carefully curated datasets created by humans, but as tasks get harder, producing these datasets becomes time-consuming and expensive. It's like trying to teach a class where the teacher has to write every single textbook. That's where self-improvement methods step in. These methods aim to reduce the dependency on humans by allowing models to improve by analyzing their own outputs. Self-improvement works in cycles. An AI model generates responses, selects the best ones based on some criteria, and then uses those examples to refine itself. Think of it as a feedback loop where the model learns by re-evaluating its own work. This isn't a new concept. Approaches like SEMGROW and RFT have been exploring it for a while. They've shown that it's possible to get solid results without relying on enormous datasets, but they've also hit some major roadblocks. After a few rounds of self-training, these systems tend to stagnate, performance plateaus, and no matter how much more data or compute you throw at them, they don't seem to improve further. The team behind BSTAR wanted to figure out why this happened. What they found is that two key factors determine how well a model can improve itself: exploration and exploitation. These terms might sound technical, but they're actually pretty straightforward. Exploration refers to the model's ability to come up with diverse, correct responses. It's about keeping things fresh and avoiding repetitive or overly narrow answers. Exploitation, on the other hand, is about using a reward system to identify the best responses and focus on those. The challenge lies in striking the right balance. If a model focuses too much on exploration, it risks producing irrelevant or incorrect results. If it leans too heavily on exploitation, it can become overly conservative, rehashing the same patterns without learning anything new. This balancing act is where BSTAR comes into play. It's a framework designed to monitor and adjust these two factors dynamically throughout the training process. Unlike previous methods that stick to fixed settings, BSTAR adapts in real time, tweaking things like sampling temperature and reward thresholds to optimize performance at every step. Sampling temperature controls how creative the model's responses are. Lower temperatures generate more focused answers, while higher ones encourage diversity. Reward thresholds determine how strict the system is about accepting responses. Together, these settings shape the model's behavior, and BSTAR makes sure they're always aligned to get the best results. To measure how well this balance is working, BSTAR introduces something called the balance score. It's a metric that evaluates both the quantity and quality of the model's outputs. The goal is to ensure the model is generating enough high-quality responses to keep learning effectively. For example, if the system selects 64 responses but only 16 are correct, the balance score will reflect that imbalance. By tracking this metric, BSTAR can make informed adjustments to keep the training process on track. The researchers tested BSTAR on a range of tasks, from mathematical problem solving to and common sense reasoning. For math, they used datasets like math and GM8K training models like MISDAL 7B. These are tasks where correctness is easy to verify. Either the answer is right or it isn't. Coding challenges were tested using the APPS dataset, while common sense reasoning was evaluated with the ARC challenge dataset, which features multiple choice science questions. Across all these tests, BSTAR outperformed other self-improvement methods by a significant margin. In the GSM8K dataset, which focused uses on math reasoning, you achieved the task at one accuracy of 53.8% compared to 46.8% with online RFT and 46.3% with Racine. For the math dataset, BSTAR scored 27.8%, a solid improvement over the 23.2% achieved by online RFT. And even in coding tasks, where models often struggle, BSTAR reached 19.6% accuracy on passage, one higher than any of the computing methods. These numbers might not seem huge at first glance, but in the world of AI, even a few percentage points can represent a major leap forward. What's even more impressive is how BSTAR maintains consistent improvement over multiple iterations. Traditional methods often stagnate after 3 to 5 training cycles, but BSTAR keeps pushing forward. This sustained growth is a direct result of its dynamic adjustments. For example, during the early stages of training on the map data set, BSTAR set the sampling temperature to 0.5 to focus on accuracy. As the model improved, the temperature was gradually increased to 1.1, encouraging more diverse outputs. Similarly, the reward threshold started high to enforce strict quality control but was relaxed slightly in later stages to allow for more flexibility. These adjustments aren't just arbitrary tweaks, they're carefully calibrated to maximize the balance score. By continuously monitoring exploration and exploitation, BSTAR ensures that the model stays on the right track. This dynamic approach is a big step forward compared to static methods like STAR, which resets the model after every iteration, or iterative RFT, which doesn't adapt its settings during training. The experiments also highlighted the importance of using additional reward models. In the case of mathematical reasoning, combining final answer matching with a process reward model (PRM) led to better results. The PRM evaluates the quality of each step in the solution, providing more granular feedback than simple binary rewards. This fine-grained approach helped retain the model's exploratory capabilities, preventing it from getting stuck in repetitive patterns. One of the most striking findings was how exploration evolves during training. Early on, the model's diversity metric increases, showing that it's generating a wider range of solutions, but without proper incentives this diversity can decline over time. BSTAR addresses this by encouraging exploration in later stages, ensuring the model continues to learn new things at the same time. Exploitation metrics like best of K accuracy show steady improvement, indicating that the reward system is effectively selecting high-quality responses. The researchers also tested BSTAR on more powerful models like Llama 3.18b. Even with these larger models, which are inherently more capable, BSTAR delivered noticeable gains. For example, it achieved 61.6% accuracy on GSM 8K and 29.2% on map, outperforming traditional methods by a clear margin. This scalability makes BSTAR a versatile tool for a wide range of applications, from education and programming to general problem solving. What sets BSTAR apart is its ability to deconstruct the self-improvement process. Previous methods treated this as a black box. You run the model through a few cycles and hope for the best. BSTAR, on the other hand, provides a clear framework for understanding what's happening at each step. By quantifying exploration and exploitation, it sheds light on why certain approaches succeed or fail. This transparency is invaluable for researchers and practitioners looking to push the boundaries of what AI can do. The potential applications are enormous. Imagine deploying this framework in areas like robotics, where machines need to adapt to complex real-world environments, or think about creative fields like writing and design, where generating diverse, high-quality outputs is key. BSTAR's ability to balance creativity and precision makes it a natural fit for these challenges. The future looks promising for BSTAR. While the current version focuses on adjusting hyperparameters like temperature and reward thresholds, there's plenty of room for growth. More advanced decoding techniques could give the model even finer control over its exploration, while dynamic reward models could make exploitation even more effective. These innovations could take self-improvement to new heights, unlocking capabilities we can only dream of today. Alright, let me know what you think in the comments, and if you enjoyed this, make sure to like and subscribe for more AI updates. Thanks for watching and see you in the next one.